Hello, Jonathan Heinrich here. I'm here to share with you today my findings from this case study from the Machine Learning Foundations for Product Managers certification curriculum from Duke University. So let's dive right in. Today, we are going to create a machine learning model in Google's Vertex AI Studio to predict the electrical energy output of this combined cycle power plant. Before we dive in, let's talk about the product management process. As with all successful digital programs, we start with the why, the business understanding, to understand what we're looking for as the business outcomes that we want to affect. Next, we want to understand our data. We want to prepare our data for machine learning. We want to combine the data features with an algorithm and hyperparameters into a modeling process, number 4. Number 5, we're going to evaluate that model. And number 6, we're going to deploy it. Specifically for today, we're going to be focused on the data preparation, modeling, and evaluation process steps specifically. First of all, the why. Without getting too far into the details, we can understand how higher efficiency leads to lower fuel costs and higher revenue for a power plant. In this case, the business value is quite clear. So let's talk about our data. So looking at the features, which are the column headers, these are the variables that contribute to the last column, which is the target, in this case, electric output. Our goal is to create a model where we can enter hypothetical feature values like ambient temperature and pressure, for example, and see how that affects our energy output. We'll need to create a few different models, carefully monitoring them against evaluation criteria in order to see which one is the most accurate. For this case study, we'll look at two different combinations of features. I'm going to run one model with the full feature set and a second model with just AT and V and see how that affects our output. Now that we've identified the data, let's prepare the data. For purposes of brevity, let's assume the sample data has been cleansed and does not contain any erroneous outliers. It's important when we train a new model that we keep some data out so we can validate our model from an objective point of view. Okay, time to roll up our sleeve. Let's talk about what a model consists of. Model consists of three different aspects: the algorithm, we have the features, and we have the hyperparameter values. When we get further into model tuning, we use gradient descent to use our learning rate to test different combinations until our cost function is at the minimum, which is shown at the bottom of the graph here before it starts to go back up. For this problem, I chose to use tabular regression modeling in Google's AutoML. For output matrix, I'm going to use the mean absolute error, the mean absolute percentage error, RMSE, and R squared, and we'll use these as we get further into fine tuning. So let's get into the tool and start to model. First, I'm going to create a bucket in cloud storage and upload my sample data as a CSV file. I chose tabular regression as we are dealing with continuous variables. Now it's time to train the model. Note that Google's AutoML automatically saves 20% of the data for test and validation. The target of our model will be PE, which is the net hourly energy output. And I'm just going to use 1 hour of compute budget here. After running my first model, I see a couple statistics here. I see that ambient temperature and exhaust vacuum are more important. I see some initial evaluation criteria. It gives me a good place to start. So we have something to compare to. Let's create a second model. We'll go through the same process that we used to train the first model. We're going to generate new data in a CSV file. I'm going to skip ambient pressure and relative humidity. I'm going to upload to a bucket in Google Cloud Storage. We'll create a second data set in Vertex AI. Okay, so let's take a look at how this turned out. Again, we're looking to minimize this cost or loss function. So now that we've got two models to look at, let's look at the criteria. I see, despite AP and RH having less effect on the accuracy, model 1 that includes them is more accurate across the board, as shown by the figures in green. Therefore, let's move forward with model 1. Final step here is to deploy the model so we can use it to experiment with inputs and predict the output of our power plant. In the model registry in Vertex AI, deploy the model to a new endpoint. Once the endpoint is deployed, we can add values to our features and see what the model predicts for energy output. Here are a few I've done. And then if we go into the actual model here in Vertex AI, let's try something else. Put in 25 here, 55,111, and 78 for relative humidity. And we're going to predict, and we see over here, the prediction result is that we get 441.28 as the predicted energy output from our power plant. We identified the modeling approach. We built two different models using different features and the same algorithm. We evaluated the models against our metrics. We interpreted the model by monitoring our error metrics, and we tested it out with new variables to see how this model could affect the business case of our new power plant. Any questions? Please let me know. Thank you very much.